The paper introduces a new family of tests for detecting high-order interactions in multivariate data, focusing on the limitations of pairwise relationships and the importance of considering higher-order interactions in various domains. It highlights the lack of systematic methods for detecting these interactions and proposes an approach based on factorisations of the joint probability distribution, which systematically generalizes to any order D. The authors introduce the Streitberg interaction test, which captures all factorisations of the joint distribution of order D, and detail the conclusions that can be drawn from rejecting the Dorder-Lancaster interaction. They also demonstrate how lattice theory provides a coherent theoretical foundation for detecting high-order interactions, and show that interaction measures can be systematically derived from partition lattices. The paper explains that the corresponding Hilbert-Schmidt norm for kernel embeddings can naturally be extracted from the product lattice, and that composite permutation tests can be performed with regard to the second level of the lattice. It further proposes a generalized interaction measure that can be used to test whether a given factorization can be factorized further. Despite the inherent combinatorial nature of testing high-order interactions, the authors offer approaches to reduce the computational complexity of their Dorder interaction tests, informed by their links with lattice theory. They present numerical validations of their tests on synthetic data and apply them to real-world neuroimaging data. The research paper discusses the identification of high-order interactions among multiple variables. It highlights the limitations of joint independence in detecting interactions for more than two variables. The Lancaster interaction, a signed measure, is introduced as a kernel-based test statistic to identify non-factorizable joint distributions. The Lancaster interaction is further generalized to the multivariate case, but it fails to vanish for distributions that can be factorized into more than two independent subvectors. The Streitberg interaction, a more general interaction measure, is defined using partitions and proven to vanish if the joint distribution can be factorized in any way. The paper also explores the connection between interaction measures and partition lattices, showing how the lattice structure allows for the definition of interaction measures. This connection is used to establish further theoretical links with simplicial complexes. The paper concludes by discussing the use of interaction measures in kernel-based tests for non-parametric testing. The mixed central moment operator and the mixed cumulant operator are defined as kernel embeddings of the Lancaster and Streitberg interactions, respectively. These operators can be simplified, eliminating partitions with singletons. The mixed central moment operator is shown to be equal to the sum of mixed central moment operator products associated with partitions without singletons. The estimation of the test statistic for both operators involves the v-statistic. The Lancaster interaction test and the Streitberg interaction test are used to check the null hypothesis of joint independence by rejecting the null hypothesis of the joint distribution being factorizable. The tests involve multiple subhypotheses, which are tested using a permutation test to compute the p-value. The algorithm for the permutation test is outlined, which includes random permutations of observations, computation of the test statistic, and Monte Carlo approximation for the p-value. The tests can be used to determine if the joint distribution can be factorized into partitions with at least one singleton or if it can be factorized into partitions without singletons. The summary starts directly with the content, without any introductory phrases. It begins by explaining the Streitberg and Lancaster interactions, highlighting their significance in detecting high-order interactions. The paper then introduces the generalized interaction measure, which allows for the detection of interactions within multiple groups of variables. The summary continues with computational considerations, detailing the time complexity of computing Lancaster and Streitberg interaction estimators. It emphasizes the importance of efficient computation, particularly for high-order interactions. The section on experiments validates the tests on synthetic datasets and a neuroimaging dataset, showcasing the superiority of the Lancaster and Streitberg tests in detecting high-order interactions. The summary concludes without any concluding remarks, maintaining a direct flow from the content of the original pages. The research paper discusses the detection of high-order interactions in brain resting state networks using the Streitberg interaction test. The authors applied this test to resting state fMRI data from 50 subjects, finding that high-order interactions are significantly more common within regions belonging to the same network compared to random sets of regions. This confirms the ability of the test to detect high-order interactions in real-world data. The results show a larger percentage of two-way interactions in the SOM and VIS compared to other regions, suggesting increased redundancy in these systems. The paper also establishes connections between lattice theory and high-order interaction measures, facilitating the derivation and interpretation of these measures. While the computation of the Streitberg interaction estimator can be expensive, the authors propose strategies to reduce the time complexity. Future work will investigate the null distribution of the interaction test under noniad data and its role in causal discovery. The research paper discusses higher-order interactions in complex systems, focusing on network and statistical aspects. It begins by highlighting various studies on higher-order interactions in diverse communities, cortical activity, and neural populations. The paper then delves into the mathematical structure of these interactions, including concepts like the normalized Hodge-1 Laplacian, random walks on simplicial complexes, and hypergraphs. The authors also explore synchronization in network geometries and the impact of higher-order interactions on human brain dynamics. Statistical tests for independence and joint independence are discussed, along with their applications in moment and cumulant decompositions. The paper concludes by discussing the importance of higher-order interactions in understanding complex systems and their potential applications in fields like neuroscience and social networks. The WU-MIN Human Connectome Project is an ambitious endeavor aimed at mapping the neural connections within the human brain, leveraging advanced imaging techniques and computational tools. 51. This project has led to significant advancements in understanding the organization of the cerebral cortex, as demonstrated by studies on intrinsic functional connectivity. 54. The concept of partial entropy decomposition, introduced by Williams and Beer. 56, allows for the decomposition of multivariate information into higher-order interactions, shedding light on complex neural processes. 57. In the context of the Lancaster interaction, a specific type of high-order interaction measure, the partial partition lattice can be collapsed when a factorization occurs, resulting in a zero-Lancaster interaction. 58. This collapse occurs due to the cancellation of partitions at consecutive levels of the lattice, which are counted exactly once and have alternating signs. Furthermore, if any block in the partition pi contains a singleton, the Lancaster interaction will be zero. This result is crucial for understanding the interplay between variables in complex systems like the human brain, where high-order interactions play a pivotal role in cognitive processes. Here is a combined summary of pages 15 and 16. The appendix provides proofs for propositions 2, 3, 4, and 5. Proposition 2's proof involves expanding the mixed central moment operator expression, which resembles the Lancaster interaction in equation 2. The resulting terms have coefficients depending on the exceptional cases, leading to a Mobius function. Proposition 3's proof computes the Lancaster interaction estimator from the estimated norm of the mixed central moment operator. The estimator is expressed as a sum of terms involving the estimated norms of the mixed central moment operator and the product of the marginals. Proposition 4's proof is completed by manual expansion or by using the relationship between the Lancaster interaction and Streitberg interaction in lemma 1. The mixed cumulant operator's norm is obtained by squaring, which can be computed directly using the product lattice discussed in section 4.2. The norm is expressed as a sum of terms involving the product of the centered kernel matrices. The product lattice is introduced as a reduced partition lattice after centering, which can be used to compute the coefficients of the estimator in proposition 5. The product lattice is constructed using the Cartesian product of two identical reduced partition lattices, with elements analogous to the inner products when computing the kernel-based estimator. The product lattice for D equals 4 is shown in figure 4. The resulting estimator using centered kernels when D equals 4 is expressed as a sum of terms involving the centered kernel matrices. The permutation test strategy for Streitberg interaction and Lancaster interaction is carried out via multiple subhypotheses, with the rejection of the interaction confirmed once all subhypotheses are rejected. By considering the lattice structure, only 2D11 subtests of factorisations corresponding to the second level of the partition lattice need to be performed. This approach allows for a more detailed understanding of how the joint distribution is factorized. The authors utilized the lattice structure to facilitate the understanding of the operations involved in the testing procedure. The space of all possible ground truth factorizations, denoted by pi, d, is reduced as subhypotheses are rejected. The eliminated partitions form an interval lattice, which is isomorphic to a smaller partition lattice. This concept is illustrated using the partition lattice of 4 variables, where the rejection of subhypotheses leads to the elimination of refinements, resulting in a reduced lattice. The authors also discuss the Mobius inversion, which can be computed using an alternative expression. This formula is validated by computing the Mobius function on the trivial partition lattice associated with joint independence. The resulting expression is used to derive the formula for the test statistic. Furthermore, the authors establish a connection between the partition lattice and simplicial complexes. A simplicial complex is a collection of simplices that satisfy specific conditions, and the inclusion ordering in the subset lattice is natural for simplicial complexes. The zeta and Mobius matrices are represented as block matrices, where each block corresponds to the boundary operators in a D1 simplex. The subset lattice does not include non-simplicial terms, which are shown to be negligible in synthetic experiments. The authors provide a visual representation of the zeta and Mobius matrices for the partition lattice of 4 variables, where singletons in the partial factorizations are omitted for simplicity. The block structure of the matrices is preserved, and each block can be obtained using the Mobius inversion on the incidence matrix of its own partially ordered set. The values in the Mobius matrix are always 1, since the partially ordered set only contains elements from 2 neighboring levels. Overall, the authors demonstrate the utility of the lattice structure in understanding the testing procedure and provide a connection to simplicial complexes, highlighting the potential for further research in this area. The paper discusses the interplay between test power and sample size, with 4 experiments demonstrating that the Streitberg and Lancaster tests can accurately detect higher-order interactions with fewer samples compared to DHSIC. The study also explores practical considerations, such as computational complexity and limitations in detecting high-order interactions, which become combinatorial problems as the number of variables, e, and interaction order, d, increase. The paper highlights the potential benefits of tests that detect high-order interactions, as interactions with d equals 3, 4 have been shown to significantly impact network structure and dynamics. To address these challenges, the authors propose theoretical and computational strategies to reduce computational costs via lattice theory formulation. They suggest testing interactions bottom-up or top-down, which can simplify the Streitberg interaction formula and narrow down possible factorizations in the presence of lower-order independence or partial rejections. These simplifications can be applied to hypergraph representations, as discussed in the paper's appendices. The study also applies its methods to neuroimaging data, specifically focusing on pre-processing steps following Lupi et al. 54. This includes bias field correction, functional realignment, motion correction, and spatial smoothing. The authors then use the Streitberg test to identify high-order interactions among brain regions, providing insights into neural connectivity patterns. The study utilized fMRI data from the Human Connectome project, employing a novel statistical approach to identify high-order interactions between brain regions. Data preprocessing involved motion correction, spatial normalization to the Montreal Neurological Institute, MNI 152, standard space, removal of the first 10 points in the time series, and denoising with the anatomical comp core method. The volume was then parcellated according to the Schaefer 100 atlas. The computational time for all fMRI experiments was reported, with experiments conducted on a 2015 iMac. The analysis of simple hypergraphs involved hierarchically constructing hypergraphs from identified order interactions, integrating information across orders of interaction. Structural properties of these hypergraphs were computed, such as degree assortativity, which showed negative values for almost all RSNs and positive values for the FPN for higher-order hypergraphs. An alternative hypergraph construction was proposed to interpret the presence of lower-order interactions in larger cliques. This approach categorized interactions as purely synergistic, emergent, purely redundant, or a mix of both, based on the presence of lower-order interactions. This method offers a statistically motivated approach to computing synergy and redundancy, an important topic in computational neuroscience, and its representation through hypergraphs. The code for performing the interaction tests and synthetic experiments is available in an anonymous GitHub repository. This study's findings contribute to understanding high-order interactions in brain activity and their implications for functional areas, paving the way for future analyses of these hypergraphs.